Okay, this is a Sorensen DCS600 volt 1.7 amps DC power supply. It's a switched power supply which I picked up from a flea market. Of course, it was in pretty bad shape. I had components burned all over here, like a couple of resistors, few capacitors. I had a totally blown trace on this side of the PCB and few random components which were also burned. I was not sure if I could fix it because the latest schematic for this specific release is not available. So kind of spent a week trying to figure it out, and it's up and running. So we power it up, and there you go. It comes to life, and let's push the voltage. I don't have a load yet, which I will connect it soon. But now it's pumping all the way up to 600 volts DC. Well, slightly above, and it's coming out through this connector and going out to this multimeter, about 608 volts. Okay, that's with some load on it, about 20 milliamps just to test it, and 282 volts, kind of slightly off from the multimeter, but I haven't calibrated it yet. And you can see there's a resistor being cooked right there. So I haven't tuned or adjusted all the trimmers to get the right readings, but it seems to be all good. It's cooking pretty well with about 20 milliamps. So let's see how this thing works. What exactly is inside this? So the input power comes in via these connectors and gets into the standard EMI filtering, common mode choke, filtering, and comes in, goes all the way into the main front panel connector. And there's a breaker here, and that just comes all the way into the main filter circuit. So there are some rectifiers out here, and it gets rectified and comes in as DC into this bank of capacitors right here. And that DC voltage will be anywhere up to 300-350 volts. Now you can see a fuse here for the main line. These are the bleeder resistors for the capacitors so that they get discharged when you power it off. Plus, this is the relay which actually clicks in. This has been built to ensure that the surge current when you power it on doesn't blow the fuse off. So the way it works is there are two resistors, I guess these two guys, they actually sit in series to the capacitors, slowly charge them up, and until they reach a specific voltage, the relay doesn't click in. And once the relay clicks in, it bypasses the capacitor and gets them in. I'll explain that in the schematic as well. Now, that's where it goes in all the way till here into this main fuse. And this is the gate to the switching circuit. So if you're troubleshooting this, if your system is not powering up, the first thing you have to do is take this fuse off. Do not work on it with this fuse on, because if this fuse is on, your main switching transistors over here, the MOSFETs, they will be powered. Okay, now this is the main power. Now to run the control logic, which is sitting all over here, you have an auxiliary power supply which is powered from this transformer out here, a whole bunch of regulators, which is standard linear regulator, which provides, I think, a +5, -5, there is a +12, and I guess there is a -18 as well, and a 6.3 volt reference. Again, I'll explain the schematic. And there is the basic circuit works around a standard PWM modulator, which is this chip out here, 3846. That's a pretty common chip. That drives a bunch of transistors, which drives the main transistors out here through a driver transformer, right? And the control logic basically makes sure that you have a linear voltage control. It's a sampling standard op-amp based regulator. So you can see the whole bunch of op amps out here, 358s and other different varieties, which are basically used to compare the output and regulate the width of the switching pulse, in turn regulating the voltage. So other than that, what you have here is a CMOS switch, which is used to control or signal a couple of inputs. There are two protection mechanisms built into it. Actually, just one basically. There's a over voltage protection, which kind of comes in and shunts the output and shuts off the PWM in case of an over output voltage. And there is of course current monitoring. So this resistor, this is the current monitor shunt. It's a Kelvin sense resistor with 4 legs, and that all goes into the control circuits to sense the output current and regulate the width. So this guy drives a bunch of small tiny transistors and through a transformer, which in turn drives the big boys out here, which switches the output, which gets filtered, rectified and filtered through this and comes out here and goes into the load. And remember, there is a specific connector here which has got a specific jumper settings to make sure that this unit works. You can configure this unit in different modes, single remote control, blah 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 blah. So just make sure that you have this thing on, or you wire a connector with the specific orientation as mentioned in the manual. Okay, now what are we looking for here? Of course, to troubleshoot, you have to start with the linear section of the whole board, just to make sure that the control circuitry has got all the right voltages, whatever it needs. So you can check the voltages around the linear regulators on this place, or look at the VCC pins of these chips to ensure that you're getting the correct voltages. Once you're sure that that's up and running, you can come here and straight away look at the pulse width modulator chip or the SMPS controller to see if it's actually switching. Remember, take out this fuse before you do any of that. Okay. There's one more thing which you need to be very careful is the over voltage protection MOSFET. Now in this specific unit I have removed it because it was blown, but it actually sits right here. You can see that this unit is on. If I touch it, I'll be fried. So this is removed because it was of course burned, because you can see this resistor was cooked, because the issue with this unit was the over voltage protection circuit was bad and this current sense resistor was bad as well. Now if you want to check the switching circuit, remember this is main lines filtered. What you see here is a main line filtered voltage, but this is floating off this transformer, the linear power supply. So whatever you're measuring here, just make sure that you don't plug anything to the mains. The ground for the linear control is available on this portion of the circuit. Probably one of the simplest places to look for is right over here, the CR1, which is a Zener. In the schematic I'll show it here. This is where you can use this. So let's see the switching powers. Let's go through the schematic and look at some of the key components in this. Now, this is not the schematic for this exact model. This is for something called as DCS, same model but without the E extension. So I'm not sure what's the difference between both of them. I asked them for the latest schematic and they won't share it, of course, due to intellectual property reasons. But I was kind of able to walk my way through this unit with this old schematic. This is available in internet. I'll put it in my blog as well. So as I explained, this is where the power comes in. Through this and the common mode chokes and protection and the main switch, it gets in here. And then from this point you can see this is the main rectifiers, and which charges these capacitors, which is basically in this unit as a bank of capacitors. So that's probably one difference you can see it start with. So that portion is what I explained before. The input comes here through the filters, capacitors, goes into the main power switch, and then from the power switch gets into the rectifier and jumps into these capacitors. Now before it hits there is a little bit of in current or inrush current limiting. So the way it works is, if you see this, there's a tiny relay sitting here between the main power line and the rectifiers, which is this guy here. Okay, now that guy is actually powered by the linear power supply here. So if you can see the schematic, there's a transformer here which is for the linear power supply. It has got its own rectifier, filters and all of the stuff. And if you look out here, out of this regulator there's a small RC circuit sitting here which is going to charge this MOSFET and control this relay. And that relay, when it turns on, directly connects the mains into the rectifier. Until that happens, the power to the rectifier goes via these resistors, so that it's kind of, you know, controlled and it doesn't have a rush going in there, right, this path. So that's what you see here in this relay, and this is the main capacitor bank, this whole portion. And I said before, this is the most critical fuse which you have to remove first before you work on it, assuming your filter, the main filter and the rectifier is good. That is this guy. So if you see this output is filtered, and this is the main fuse which drives your main switching MOSFETs all the way down here. Some of the other key components in this, as I said this before, this is the main PWM controller. This is the current sense shunt resistor. This is the resistor which is R93 in the schematic, which shunts across the main output in case of an overload, and that is done by a MOSFET which is supposed to live here, but I have removed this because it's broken in my case. Now this is a Kelvin sense resistor with 4 leads, and the sense leads are going directly to the, you can see this was blown in my case, they go directly into the op amps to control the width. Now the schematic, this is the closest, like I said, I could get. It's kind of very similar. There are some additional components, or some cases this schematic is slightly different, but more or less it's the same. So this is the switching regulator. As you can see, 11 and 14 goes out into this driver transistors, which drives the main MOSFETs through a driver transformer, right? And then of course there are control circuits around it to control the width of this modulator. These are the low voltage regulators out of the auxiliary power transformer, which provides various voltages like -5 if I'm right, there is +5, there is +12 as well, and it's a standard 3-terminal regulator what they've used. This is the critical piece which you need to watch out for. This is the over voltage protection drive. So this op amp drives the final voltage or final control signal for the over voltage protection. What it does is it fires this transistor, which is this little puppy out here, this guy that was blown in my case. Okay, and where am I? Okay, so it comes here and goes out and drives this main shunting MOSFET and to R93, which kind of shunts the entire output. At the same time, the control logic makes sure that this voltage, the drive voltage, is also fed back through this into the PWM so that it shuts down the SMPS. Now, as I said earlier, in my case, this was kind of half cooked. It's still alive, but the MOSFET was totally cooked because the switching circuit here was bad. This circuit is kind of standard op amp based comparators, or voltage measurements. Basically, all of them sense the output voltage and current. So this is the output current sensing scheme, which you can see here. This is the Kelvin sense resistor here, this particular guy, and that voltage comes into these op amps, and then they drive the controller, the SMPS controller here, to regulate the output or shut it down completely if needed. In my case, this was open, and that was driving the whole 600 volt into this section, cooking everything around here. Right. Now, another piece is interesting piece which you need to look for is the over voltage protection circuit. Ideally, if you start working on it, the first thing you may want to do is to take this MOSFET off or check it, just to make sure that it's not bad and sitting there just short circuiting the output. Now, the over voltage protection circuit, that's something interesting. So there are current limiters and voltage limiters all over the place. Again, basic op-amp circuits, there is nothing fancy. The CMOS switch is used in a whole lot of parts of the circuit to switch or control the input, which you can see here as this symbol in the schematic. This is the CMOS switch, which is a CD4000 series chip here. You can see this guy. Okay, let's look at the over voltage protection. Now, this is controlled by this op-amp here, U32 to be very specific, which is all the way sitting here. This little guy here, he controls the over voltage protection. The way it does is, as usual, it has got a input control, which is right down here in the schematic. That sets the protection trip level, which is right here in the front panel. And that is coming here, providing one input to the op-amp. And of course, the second input is from the output, which is sensed all the way from the final output circuit, which you can see all the way going in here. Now, what happens is if the output exceeds the preset level, it's gonna preset level of ratio, whatever is the input output to expected output ratio. This guy will go high, which in turn is going to drive this MOSFET, which will drive this MOSFET, which will drive this guy and shunt the output. That's one action to make sure that the output voltage goes to 0 as soon as possible. And the other action is he's going to actually drive this output all the way till here into this, which is the disable line for the PWM, so that the SMPS also gets shut down right away. Circuit is, as I mentioned before, fairly straightforward. You have different sets of op-amps to compare various voltage levels and current levels and sense it and control the width of this PWM controller. In case if you are troubleshooting, the best way to set up a simple op-amp inverting or non-inverting amplifier and check these op-amps just to make sure that they're all good. And like I said before, never try to play around with this thing into the circuit unless you're already done with rest all troubleshooting and you're sure that this guy is sending pulses on pin number 11 and 14. That's the drive output. Another point around the capacitors, I haven't really checked the ESR of these capacitors. So do these guys around here. I haven't really checked them to make sure that these guys are okay or not. I assume they are okay, but I'm going to check the ripple at a later point and see if it's really good. In case if these guys are dried up, or this one or this one, if they are dried up, you may have to replace them to get a better ripple, or a lower ripple in the output. So just be careful of these things, and different models do come in with different set of capacitors, but hitting at the same value. Another point, be very careful of this pin here. This is the rectifier DC, so do not touch it. A quick point on the over voltage protection circuit. Now this is not monitoring the output voltage what is set here. Okay, this is actually presetting a voltage as the output voltage. Say for example, if you turn the port to a specific value to set the over voltage as anything about 200, the moment you increase the output voltage to 200, it'll trip. So it's not monitoring the dialed value and then triggering the over voltage. It is actually setting a preset value and just making sure that the output never exceeds it. So this is useful in a scenario where you're just doing some testing and your maximum voltage is supposed to be, say, only 200 volt. Then you set it to 200 volt on the main panel and then adjust the over voltage protection until it trips at that value, or slightly above that value, to make sure that your output, and no matter what, it doesn't exceed whatever you want. Otherwise, by accident, if somebody turns this, it can actually go above whatever is the value which you want. So this is just an additional protection, but you need to be aware of this control, otherwise it can confuse you by shutting down the unit.